an annual event. I think it's gone on for about 4 or 5 years now that we've hosted a Christmas lecture by a member of staff at the Institute of Cosmology and Gravitation at Portsmouth University. And this evening, I'm very delighted that we can welcome Professor David Wands, who's actually director of the Institute. And I'm going to let him introduce himself really and say what his background is and tell you a little bit about the Institute, because I'm sure he likes to show it off, because it is quite a remarkable place, and I'm very grateful that they actually gave me the opportunity to spend 6 weeks with them in the summer term on a sabbatical placement, and to experience what it's like to be in the environment that they work in, with lots of international researchers there, and also to take part in the National Astronomy meeting, which they hosted this year in Portsmouth, which was very exciting. So this evening, Professor Wands is going to talk about a very current research topic, one which is in the news a lot less than a year ago, wasn't it? I think it was earlier this year, and that is this signal which has been detected by the telescope at the South Pole, and then the controversy as to whether that was an indication of the final proof of the sort of inflationary epoch in the formation of the universe, or whether it was a signal caused by background dust, which is still being investigated. And I'm sure he's going to tell us a little bit about that this evening. So I'll hand over to Professor Wands. Thank you very much.
Thank you very much. Thank you for that introduction. It's a pleasure to be back here in the grammar school. As Jeremy says, we've got strong links over a number of years now with the grammar school, and more broadly trying to sort of take out and bring to the local schools something about the physics, the scientific research that goes on in the university, and in particular the institute where I work, the Institute for Cosmology and Gravitation. So I'm going to tell you a bit about the universe, how the sort of research that we do in Portsmouth into the large-scale structure of the universe, so what the universe actually looks like on the largest scales, how we map those and trace the structure in the universe on the very largest scales we can see. And in particular, I'm interested in what that tells us about the period in the very early universe, at very high energies, the idea that there may have been a period of rapid expansion, accelerated expansion called inflation in the very early universe, and the reasons we learn about that through structure that we see in our universe. So, as I say, we do this at the Institute of Cosmology and Gravitation, just across the road in the university. In fact, in this nice building, Dennis Sharma building, we opened a few years ago. The Institute was established really from a research group in the mathematics department originally, but myself and many others there are actually physicists by training. But we work at the boundary often between mathematics and physics in modelling the universe. And as well as teaching undergraduate units in physics, maths, even in maths for engineers, and increasingly into astrophysics, as of next autumn, next September, we'll be recruiting our first students in physics, astrophysics and cosmology. So we teach the familiar undergraduate subjects, but we also research, do scientific research, publishing papers, contributing to international collaborations in cosmology and astrophysics. And we've now got more than 50 academic staff and postdoctoral researchers and PhD students. PhD students are the students who are still working when the undergraduates have gone home, because they've got 3 years or 4 years to work on their postdoctorate, their doctorate. And the postdocs are people who, even once they've finished 3 years of a PhD thesis, still want to carry on researching and learning more about the universe. And indeed visitors from around the world. So this is a picture of us a few years ago at the opening of the Dennis Sharma building just on Burnaby Road. And we're lucky that we get to spend our days thinking about the big questions in science. The universe on the big scale, The biggest bound structures are galaxies and clusters of galaxies in our universe. So my colleagues study the properties of galaxies and how we can learn about how they were made, how the stars in them were formed, and what the important physical processes are, how galaxies merge, the role of massive black holes, supernova explosions in galaxies. And my area is really, if we put all that together, we use galaxies as tracers of the dynamics of the universe. And through that, learn about what the universe is actually made of. So the stuff you can see, the visible light, but also the dark stuff, dark matter, and dark energy you may have heard of. And in particular, what I'm going to talk about today, how structure emerges in the early universe. And through that, we learn about the laws of physics. We interpret the structures and dynamics that we see with the physical laws that we understand, and then we extrapolate them to even higher energies, to even earlier times, and see how we can learn through the physical models that we build up, how the laws of physics may change with time or scale in the universe, how gravity may change, how do we incorporate the ideas of quantum theory and gravity, even extra dimensions. So I'll touch on some of these things today, and I hope I'll leave you some time to ask me questions about the things I don't say. But let me start with the business of actually looking out through telescopes, like this telescope in New Mexico, to build up maps of the galaxies in our universe. So we're looking over millions, billions of light years out into space. Telescopes like this build up the biggest maps of galaxies in the universe. This is the Sloan Digital Sky Survey, just some of the galaxies mapped out here as you look out from our vantage point in the universe. Each dot you can see here is a galaxy. So remember, a galaxy is maybe 100,000 million stars. That's one dot. And then you build up all those dots. And you look at the map of the universe you can see. And you see galaxies in pretty much every direction you look. But there are structures that emerge, great walls and filaments, as they organize themselves, as they cluster in the universe. And if you want to see some galaxies yourself, you can go to a website like galaxyzoo.org, where you can get involved in actually identifying and classifying the different types of galaxies that are mapped through with surveys like the Sloan Digital Sky Survey. These are big collaborations. This involves hundreds of scientists from around the world. There are 43 institutions around the world. 22 of them are full institutional members, and the one UK full institutional member is the University of Portsmouth. So around the astronomical world, Portsmouth is known for its involvement in surveys, big galaxy surveys like the Sloan Digital Sky Survey. And as you may know, what we find is when you look out at the galaxies around us, they're moving away from us. So on average, the further a galaxy is away from us, the faster it's moving. And this is the remarkable discovery made by Edwin Hubble here in the 1920s. He plotted basically his estimate of how far away galaxies were against the recessional speed, the Doppler shift of light from the galaxies that he saw, and fitted it with a straight line, and that constant of proportionality became known as the Hubble constant, which tells you about if galaxies are moving away from you proportional to their distance, the simplest explanation is simply that space is expanding. So this was a remarkable discovery in the early 20th century. And it actually came after a remarkable theoretical framework was set up to describe concepts like the expansion of space. And that was Einstein's theory of general relativity. In 2015, it will be 100 years since Einstein proposed his general theory of relativity. And that was his theory of gravity as a theory of space-time. So the framework we use when interpreting this Hubble expansion is the mathematics of general relativity. And well, I won't give you too much of the mathematics. I'll give you the nice sort of summary of how general relativity works. It's that really space and time are a four-dimensional quantity continuum that tells matter how to move. So matter, the galaxies move simply through, they follow basically straight lines in effect through space-time, and space-time tells matter how to move, but gravity, space-time is itself a theory of gravity, so it is the matter, the gravity of matter is what's telling space-time how to curve, and that's the manifestation of gravity in Einstein's theory. And it was a truly remarkable sort of theoretical construction, and it still is 100 years later. We find it very difficult to come up with other theories of gravity which can really compete in order to describe our universe. It tends to be the theories of gravity that go beyond general relativity that work theoretically, self-consistently, actually turn out to be very similar to general relativity. And if you make something which is very different from general relativity, often it often just doesn't work. Yeah, this is a mugshot of Einstein, if you can see that. And there's a nice quote I got here from when someone asked him, how do you come up with these things? And he said, in very sort of Einstein quote, well, it's my disposition for abstract and mathematical thought, as you might imagine. But he also said, and in a very sort of self-deprecating way, it's also my lack of imagination and practical ability. So some of us lack imagination or practical ability. We become sort of theoreticians, and we dream of emulating this wonderful sort of theory of gravity which Einstein came up with. We'll show you a little bit of maths, a sketch as to how general relativity works in cosmology. The model of the expanding universe was developed soon after Einstein's work by people like Alexander Friedmann here, and he realized that Einstein's equations of general relativity really gave you a way of understanding a dynamical cosmos, and with an expansion, what we now call the Hubble expansion, and the equations tell you basically how matter, remember matter tells space-time how to curve, so the density of matter drives the expansion of the universe. You also have to consistently include the spatial curvature of the universe, and there's also a famous constant that turns up in the equations. There's sixth formers here doing integration in their A-level maths. Well, this is an integration constant that you have to include in the equations. So this is an example of how the space-time, or in this case the spatial expansion, the Hubble expansion rate is determined physically by a theory of gravity like general relativity. And the simple result, which I'll come back to again throughout the talk really, will be that the Hubble expansion rate is determined by the density of matter in addition to other quantities like curvature and a cosmological constant. So we'll hopefully try and use that in modeling the universe around us. So we have this picture of an expanding universe. We can map out galaxies over billions of light years, and you might ask, well, so how far back can we look? Why stop at billions of light years? Why don't we just keep going further and further back? But it's because of that expansion, that dynamics, that dynamical state of the universe, that there is a limit to how far we can look back. And that's because if we trace follow the expansion back, so back in time, the universe was smaller and smaller. It becomes denser and denser and hotter. And there comes a point at which it's so hot and energetic that atoms, the electrons and the nuclei in atoms, are no longer bound. They scatter and rescatter, ionize, and into a hot plasma. And if you've got a charged plasma, that's basically opaque to light. So light can only travel freely through the universe after about 300,000 years after the Big Bang. So we can see back tens of billions of light years, but then eventually we get to an opaque surface. And so the analogy shown here is it's like looking up on a cloudy day. How far out do you see in the sky? Well, you see to a surface which is the bottom of that layer of cloud. Actually, it's been far too sunny today for this, but the clouds that you have seen, how far back do you see? You see the surface of the cloud. And that's true in the universe, that the universe gets opaque, like the surface of a cloud, at a certain distance from us, and that corresponds to a time back in the history of the universe when it gets heated to a temperature of several thousand Kelvin, 3,000 Kelvin, 3,000 degrees, and that's a hot surface. And today we see that as a background radiation from the Big Bang, and I think this is one of the key reasons scientists, almost all scientists now believe there was a hot Big Bang, because in the 1960s, these two guys, Penzias and Wilson, at this huge radio telescope in New Jersey, found this faint background radiation in the universe. They found it in every direction they looked. Even when they cleaned out their antenna, it was still there. And as good scientists, they did everything they could to remove this signal, but then when they found it was there, they published a paper. And in fact, they also phoned up their colleagues along the road in Princeton and said, we found this radiation in all directions. Do you know what it is? And in Princeton University had actually been trying to build a telescope to detect this radiation. It was the cosmic background radiation from the hot Big Bang. So it's 3 degrees. Today, the universe has expanded and cooled, so this radiation is just 3 degrees above absolute zero. It's tens of billions of light years away. It sets the scale, the maximum distance we can see in the universe. And the best picture is you can get of the microwave background is to go above the cloudy sky and atmosphere and go out into space. And that picture of the cosmic microwave background was revolutionized when I was a PhD student, really back in the 1990s. We got the first results from this satellite, the COBE satellite, NASA satellite. So the first thing the NASA satellite saw was in every direction in the sky, up in space, they could map all directions in the sky, and they found it was a fantastically uniform radiation, 2.7 Kelvin in all directions. They could also see what had been discovered through the 1970s, that there's actually a systematic, pretty yin-yang pattern, a dipole pattern on the sky, but that is consistent with having radiation that's uniform, but then you move in one direction, you get a Doppler shift, so you get it's hotter, and I think the color code they used was hotter in this direction and colder in this direction. And but the simple explanation is that's just because we're moving relative to the cosmic background. So it's at a level of about millikelvin, so 1 part in 1,000. That tells you about our local motion relative to the cosmic background. But what COBE did for the first time was go beyond that and began to see faint ripples from the microwave background, that last scattering surface of the microwave background radiation 14 billion years ago. And it's the blobs that you see up here and up here. It's not this hot blob that you see across the middle. So this is a map of the whole sky in all directions, but you see that there's a band across the sky in these radio frequencies, just as on a beautiful crystal clear night, if you go out into the night sky and look at the stars, there's a band across the sky. Do you know what that band would be?
Milky Way.
So that's the Milky Way, and that's the Milky Way seen on the microwave sky, microwave radiation wavelengths. a few centimeters in wavelength, you still see the galaxy there. But up away from that, we believe that most of the signal from gas and dust in the galaxy is concentrated along here. And there was, for the first time, statistical evidence that even away from the galactic plane, there were some primordial fluctuations. So this was our first glimpse of structures at the edge of time, if you like, back at the edge of our observable universe in the cosmic microwave background. So since then we've had more high-resolution picture of the cosmic microwave background sky from ground-based telescopes as well as satellites. In the 2001, the NASA launched the WMAP satellite, and I'll show you the image from that in a minute. And it also was a multi-frequency. They built up a multi-frequency pattern that allowed them to remove this galactic, our galaxy, the Milky Way signal from it. Actually, I should show you here. Actually, I don't think the slides necessarily show it. NASA were kind enough to send me a beach ball with their picture. So in fact, this is the NASA view from about 2005 or so from the WMAP satellite, where this is the sort of updated version. So this version still has on the galactic signal here. In fact, there's the galactic center. You know, it's a bit brighter towards the galactic center. But away from that, if we turn the galaxy away, these are the primordial fluctuations here. And as I say, with multi-frequency information, you can remove almost all of that galactic signal, and underneath you get a picture. Oops, let me get there. Get a picture like this. So here it is again, the sky wrapped around in a sphere now, as the sky is. We're in the center of that. So we are here, and looking out at the galaxies around us in the Sloan Digital Sky Survey. But the galaxies only map the local universe, and this cosmic microwave background sky maps, say, the edge of the observable universe out 14 billion years in the past. And we see these, but even then, we don't see galaxies anymore, but we see very small fluctuations. Now, these fluctuations are on top of a uniform background. They're fluctuations of about 1 part in 100,000. So they're very small but definite fluctuations that are seen there from the WMAP satellite. And the state of the art now comes from the European Space Agency satellite Planck. This is a multi-frequency mission. So you can see here 30 gigahertz through to almost 900 gigahertz frequency channels mapped out in even higher resolution with the Planck satellite. You see these high frequencies, predominantly the galactic emission, but they deliberately go and map out the galactic emission at these high frequencies so that you can correctly model it and subtract it from the lower frequencies, where you can see, say, at 70 gigahertz, the cleanest signal of the primordial signal here. And it's through the frequency dependence that they separate these different signals. And from that, they can reconstruct really the primordial sky, the fluctuations at the surface of the last scattering. And so you get this fantastic picture, which was released just in March 2013, the highest resolution picture that we have of the whole cosmic microwave background sky. And this is what we do, cosmology of the very early universe. This is still the state, this is basically the best map we have to begin to understand the dynamics of the universe at even earlier times. So this is when people tell you about what the universe is made of, dark matter, dark energy. Much of this information has come from these detailed maps. We don't look at individual spots on the sky as to whether they're hot or cold. What we do is we break it down into the power on different angular scales. In fact, by eye, you can see that there's a characteristic scale here. You can see that there are spots of about the size of my finger across, as I hold it up there, across the sky. So that is, and that's reflected in the angular power spectrum. That's basically the 1 degree angular scale. There's a large peak in the power. That's where the strongest variation is. You get a few secondary and third peaks out to fractions of a degree, but then the power decays away. There's not much structure on very smaller scales, and there is some structure on these very large scales, structure that varies across the whole sky. That's mapped out here at this end of the graph. And the red points are the observational data points. There's a green line here that is the predictions of the standard cosmological model. And you have a little freedom to vary some of the cosmological parameters, but there are basically 6 parameters used to draw this green line. And as you can see, it's a fantastic fit to the data points. So this is, when people talk about precision cosmology, the mathematical physical models we're working with are trying to reproduce, are so far successful in reproducing this to great accuracy, all these red data points here on the curve. You have to fit the correct value for the Hubble constant, the fractional density of matter, this strange cosmological constant term which dominates actually the expansion at present, other theoretical parameters. And in fact, and so I'm not going to talk much more about these. This is another talk where we talk about the content of the universe today. But I'm going to focus more on the other bit information you need to fit this pattern. And that is an overall amplitude, just how big are the fluctuations, and a tilt, basically what the power on the large scale is relative to the small scale. And one of the big results in the last 10 years has been realized that there is a non-zero tilt to this. It's of about a 4% tilt. So if you like, what we're doing is we're basically allowing for this kind of tilt, changing the power on large scales relative to small scales. And there's evidence for a small tilt of about 4% in the data, and that wasn't predicted before the theory of inflation that I'm going to tell you about. So this is perhaps currently the best evidence we have that there's something like inflation happening in the early universe. So we can, and the way we probe inflation is looking at the origin, these fluctuations in the microwave background sky. So we've got a fantastic model of the universe if we pick these parameters and we set up the initial fluctuations in the matter in the universe. So it just leaves a small question about where does it all come from? So where does all the matter, energy, and structure that we see at the earliest times in our universe, where does it come from? And that's where this is where the theory of inflation comes in. So if we sort of sketch here the history of the universe going backwards in time from the present day, where we see this radiation at just 3 degrees above absolute zero, 3 Kelvin. We trace it back to a time just 400,000 years after the Big Bang, a temperature of 3,000 Kelvin, we see the cosmic microwave background. But we test physics, the laws of physics, back to much higher temperatures. We go back to a million or 1,000 million degrees above, 1,000 million degrees, we get to the era of when atomic nuclei are formed, so-called nucleosynthesis. We study in collider experiments the quark-hadron transitions, so where quark soups turn into hadrons, back at, what's this? This is like 8 billion degrees above absolute zero. It's actually 1,000 billion degrees. And if you go to the LHC, and in CERN, in Geneva, that experiment is now probing 1,000 degrees higher in temperature, we go into this, in fact I've put it here in terms of the particle physicists' units of giga-electron volts, and CERN probes energies of 1,000 giga-electron volts. And inflation doesn't occur as far as we understand the laws of physics back at the temperatures of nucleosynthesis or quark-hadron transition, or even at the electroweak phase transition. It doesn't have the right properties. But somewhere between the electroweak phase transition and the Planck epoch, inflation is the idea that an accelerated expansion at times as early as this, so this is like more than less than a billionth of a second after the Big Bang, or at least after the quantum gravity epoch, then that would set up the initial conditions of our universe. So our whole observable universe at that time could have been as small as a centimetre across. But the rapid expansion you get there can create something as large as our entire observable universe. So, what is inflation? How do you produce the entire content of our universe? Well, the claim is you produce this from nothing, from empty space. So you don't have to put it all in at the start. You can just start off with vacuum, but a specific kind of vacuum, a vacuum which has an energy density even when space is empty. So this is called a false vacuum, and it might sound odd, but it's simply the statement that you can have a box of space, and once you've taken all the particles out, all the stuff in space, there's still an energy density there. So nothing itself can have an energy density, a vacuum energy. And that has the special property that, unlike ordinary matter, when the universe expands, the energy density goes down because you've diluted it by the expansion. Well, if you've got empty space, nothing there, then as you expand it, you still got nothing there, so it's got the same energy density. So the universe can double in size, the density of energy can't decrease, so you must have doubled the total energy in the universe. And you double it again and again and again, and this is the idea of inflation, the physics of inflation. So it's kind of odd, you might think. It's, for instance, this vacuum energy has negative pressure. And you can do a sort of thought experiment where you have a box of true vacuum with no energy and no pressure, and put it next to a box with positive energy density. Well, the false vacuum with positive energy density actually that's the unfavored state relative to the true vacuum, the low energy density. So the true vacuum expands into the false vacuum. And if this has got zero pressure and it's expanding into the false vacuum, that must mean that the pressure is less in the false vacuum. So indeed it is consistent that it has negative pressure. So it's an odd, false vacuum's odd. It's got energy density, but it's got negative pressure. It's unstable to decay, so it will disappear if it can travel down into a true vacuum, zero energy density state. But if the false vacuum is there for long enough, it can drive the expansion of the universe. So while other quantities, like spatial curvature, are diluted by the expansion of the universe, a constant vacuum energy can drive a constant expansion. In fact, it's just like a cosmological constant term in the equation. But this is a physical way of thinking why there's a constant term in the equation. It's this constant energy density of empty space. And if you've got a constant expansion rate, that means that the scale factor of the universe actually has an exponential growth. And it obeys the laws of physics, because the total energy in the universe increases because work done is pressure times the change in volume, and the pressure is negative. So as the universe expands, work is done on the universe. You create energy in the universe. So locally it obeys all the laws of general relativity. If you accept that empty space can have an energy. And that's what people like Alan Guth realized in the 1980s comes out of some modern field theories of particle physics. Indeed, ideas like the Higgs field. The Higgs field has a self-interaction energy which potentially can have a sort of false vacuum energy density. So you can actually think of the vacuum energy as being a function of some field, like the Higgs field, and in some states you have a false vacuum, in other states you've got less energy, you've got a true vacuum. And in the 1981, Alan Guth here proposed that this could provide the energy. A false vacuum inflation from some grand unified theory of particle physics could drive expansion at very high energies associated with grand unified theories. And he guessed that you could get from the false vacuum to the true vacuum through what's called a first order, through a phase transition. Basically, bubbles of true vacuum would appear in the false vacuum, and that would produce, would end this state of inflation and start the hot Big Bang. The only problem with Guth's model was it didn't work. This bubble picture didn't work because space was expanding so rapidly. You couldn't get a consistent model where you ever escaped. Either you escaped straight away into the true vacuum before you got expansion, or you never escaped from the true vacuum as the universe expanded. So through the 1980s and since, people have developed alternative models for the dynamics of inflation in the early universe. Old inflation, Guth's model was replaced briefly by new inflation using alternative grand unified theories where you might have a smooth evolution, a so-called second order transition to the true vacuum state. But it was very hard to manufacture. There's a lot of fine-tuning. These were quite contrived models to have a sufficient duration of inflation. Until Andre Linde here advocated the idea of so-called chaotic inflation, that you didn't really have to contrive some complicated transition. You could have a very simple model where the vacuum energy would change smoothly, but as long as you started at very high energies from random initial conditions, that would give you a slow roll, slow evolution from a false vacuum energy density to a true vacuum zero energy density. And this kind of removed inflation to some extent from the particle physics models. These were no longer necessarily grand unified theories of physics. They became field theories of inflation itself. And it's been a struggle ever since, really, to reconnect the requirements, what we need from inflation driving the early universe to particle physics models of grand unified theories and the like. So this is very much an ongoing field of research, how best to reconcile the dynamics of the early universe with particle physics models. But the dynamics of the universe itself, these very high energy inflation models, can be tested independently of the particle physics models through looking at the structure in the universe. And we do that, as I say, through looking at the properties of fluctuations we see on the microwave background. And the next key ingredient, I've not thrown enough strange concepts at you today. Let me introduce you to something else you might have heard of that plays a key role in the formation of structure in the universe. And it's beginning to combine ideas of quantum physics with gravity. And this was really done for the first time in the 1970s by Stephen Hawking here and his assistant Marilyn Monroe. This is Hawking's 60th birthday party, I think. Hawking did, again, a fantastic sort of thought experiment. and thought about what would happen if you study quantum fluctuations at the edge of a black hole, at the event horizon of a black hole. And if you consider the effect of these quantum fluctuations, so a black hole where classically nothing can escape from the black hole, light only ever falls into the black hole. Once you're inside the black hole, you can never escape. But quantum mechanically, you can have fluctuations that emerge from the horizon of a black hole and escape to infinity. And they actually take energy out of the black hole, and indeed this leads to the Hawking evaporation and decay of black holes. But to an observer a long distance from the black hole, you see quantum fluctuations, actually a thermal radiation from the event horizon of a black hole. And inflation is very similar. There's an event horizon in inflation due to the expansion of the universe. But here, we're inside the event horizon. But nonetheless, when you study quantum fluctuations at the event horizon of an inflating universe, you again see fluctuations. It's the dynamics of the space-time turn quantum fluctuations into real classical fluctuations as those quantum fluctuations travel across the universe. And so this crucial idea enables us actually to test models of inflation, because a model of inflation also predicts a spectrum of fluctuations. And we think that is exactly what you see on the cosmic microwave background sky. The spectrum you would expect to see is something like this, a Gaussian random field. So quantum fluctuations, basically maximally random fluctuations of a field, set in the inflating very early universe. These microscopic fluctuations get stretched up to become actually the large-scale structure of our universe. And so we would see density fluctuations, so fluctuations in the curvature of space-time corresponding to overdensities in the matter in space-time. And you also would actually expect to see fluctuations of the space-time itself, the free fluctuations of space-time that we call gravitational waves. So these come naturally out of the idea of inflation in the early universe. And so when we're looking at the CMB, you may actually be looking at quantum fluctuations stretched up to the largest scales we can see in the universe. And if that's true, then we see fluctuations, we're seeing the Hawking temperature of the very early universe written on the sky. And in fact, one of the predictions of so people already knew that there were density fluctuations in the universe before inflation was proposed. We'd already seen galaxies in the universe. We knew there was structure density fluctuations in the universe. Gravitational waves, well, we'd never seen them anyway. So in the last 10 years, the best evidence for inflation has really come from this tilt in the fluctuation. So you can't see it here, but if you remember when I said we fitted the angular power spectrum on the cosmic microwave background sky with a small tilt, that 4% tilt of fluctuations in the CMB sky was predicted from these chaotic inflation models, where the slow dynamics of the vacuum energy during inflation is mapped onto a small tilt in the power spectrum of fluctuations. So this was a sort of technical result, but it's the best evidence we have in terms of a prediction of inflationary theory, which was then vindicated by, found in the data, and it's now generally accepted that there is a small sort of 4% tilt at high significance in the anisotropies that we see, the fluctuations we see in the cosmic microwave sky. So this is the standard almost now the standard model of early universe cosmology. It's our best model of why there are fluctuations in the cosmic microwave sky. So let's extrapolate a bit further still. Where would this take us? So if you take seriously this notion of a vacuum energy driving an expansion at very high energies in the early universe, and of quantum fluctuations about that giving you variations in the density in our universe, then if you go back further, at even higher energies, you see that these quantum fluctuations can become large compared to the classical evolution. So inflation is the sort of inexorable increase in the scale of the universe. Well, this is actually the inflation in the gold price, I think, here. But superimposed on it, you see random. So it does go up, but there are fluctuations superimposed on it, stochastic random fluctuations. Well, this is my model for how the quantum fluctuations in pointer's going out, but anyway, the quantum fluctuations in the vacuum energy can become larger and larger at high energies. And the quantum fluctuations can take to higher energies, and at higher energies the universe expands more, and you can get a runaway behavior of these quantum fluctuations that's being called stochastic inflation. First discussed by Starobinsky and others in the early 80s, and really developed by Andrei Linde, has become the principal exponent of this idea, that indeed these quantum fluctuations can produce large fluctuations in the geometry of our universe. And it might even be that in very distant parts of the universe, inflation is still going on, but driven by quantum fluctuations. So this is actually, so you may have heard of the multiverse, which is a term used in different ways. But I think this is actually is the most reasonable way in which you expect there to be a multiverse, in the sense that you don't necessarily expect the universe far beyond what we see to look like it does here. And then inflation gives you a reason why there should be quantum fluctuations, and that could produce a very different universe. And we would be living just in one little pocket of the universe. So when we look out at the cosmic microwave background sky, we map out this little patch of the universe, but we can't learn much about the universe far away. And it is indeed possible that there's inflation expanded up the universe on a much grander scale, and that quantum fluctuations led to very different parts of the universe looking very different. So as Andrei Linde said, inflation, this creation of the universe from nothing, is not only a free lunch, but it's the ultimate free lunch, serving all possible dishes. Right? So inflation is this process of producing a vast universe and a vast range of possible universes through the quantum fluctuations. So we might see small fluctuations on the cosmic microwave background sky, but on the even larger scale there could be even larger fluctuations. So, why should you believe any of this? We see fluctuations on the cosmic microwave background sky. We want to know where they come from. There's a tilt, there's a scale dependence in those fluctuations that was predicted, a small effect predicted by inflation. But what would really convince cosmologists that inflation had occurred? Well, I think it would be the other aspect prediction of inflation, not just the density fluctuations in space-time, but the gravitational wave fluctuations in space-time. They don't have to be there. You don't need them. They don't form galaxies, and no one had ever seen them in the cosmic microwave background sky. But they should be there in inflation. They are fluctuations of space-time that would be excited by the Hawking radiation process. This is what they look like. Gravitational waves as they travel through space-time squeeze and stretch space-time in these two patterns. they're a prediction of inflation, and if you combine it with this idea of Hawking radiation, what I've written there is semi-classical gravity. How big they are depends on what the energy scale of inflation is. And if inflation's right up at the very high energies associated with grand unified theories, we might just see them in the cosmic micro background sky. And the distinctive way you would see them is they do produce temperature fluctuations, but more than that, they produce a particular kind of polarization in the radiation. It's called a B-mode polarization. So that's why there was lots of excitement in March this year when the BICEP-2 experiment at the South Pole claimed to have detected evidence of these B-mode fluctuations. These would be interpreted as that they're not produced by ordinary density fluctuations in the early universe. So if they come from the early universe, they would come from primordial gravitational waves. So there was a big press conference in Harvard on the 17th of March this year. Rumors had started going around the physics community just over the weekend before. We'd all been saying, have they really seen them? They've not been seen in the Planck satellite. Could BICEP have seen them? And then they did this press conference Monday morning, March the 17th. I was being phoned up by the newspapers, spoke to the Financial Times, and I became one of these experts who crops up all over the media when there's a news story giving their expert opinion. So I even found myself on a BBC News channel, Big Bang evidence, major findings on first moments of the universe. It was big news, and it was big news for scientists that BICEP-2 claimed to have found primordial gravitational waves, smoking gun evidence for inflation. They'd been collecting data from this telescope at the South Pole, the BICEP experiment, suitably cold and noise-free as you can get on planet Earth. They'd looked up, you can't see the whole sky from Antarctica, but you can see a patch of the sky away from, here's the galactic dust emission. They found a patch of the sky far away from the galactic plane where they hoped you had a fairly clean, you had the cleanest signal they hoped of the cosmic micro background sky you could see from the Earth. And they found this, when they analyzed it, they extracted this B-mode polarization pattern. So polarization is the alignment of the electromagnetic field, and this B-mode is a kind of so-called curl polarization distinctive pattern. They even studied the angular power spectrum of it and compared it with theoretical predictions, and they found a whopping great signal, about twice as big as we thought was allowed